Hello. Last video we calculated the photon self-energy at one loop, right? This is one of the three loop calculations I want to do for QED. But before we move to the next one, I want to take a look at the physical effects generated by these correction to the photon propagator. So today we're looking at the physics of the 1pi function, right? And what we obtain for this function at one loop is the following expression, right? So this is the constant in front of the Feynman parameter integral. Remember, this is proportional to e squared, right? And the loop expansion in QED will give me powers of alpha, right? So we have e squared, e to the fourth, e to the sixth. So the real expansion parameter is really this alpha, right? Here is the integral in the Feynman parameter. So we have x, 1 minus x. And after renormalizing, we got this log right here, right? M here is the mass of the electron. And we want to see, and Q square here is the momentum of the photon, right? And we want to see a few effects generated by this correction to what you had, just the free photon propagator. So in order to do that, let's see how this Q square here behaves in a few situations, right? So my time is flowing to the right in these diagrams. And what happens here? Now I'm thinking of a scattering of on-shell electrons in all these cases, right? Is that on the T and the U channel, Q square is always smaller than 0, right? And in the S channel, Q square is always bigger than 0, right? We saw that in quantum field theory 1. But you can easily show that just using momentum and energy conservation from this initial momenta going, right? And that means that, let me copy this expression here, right? That in the case where Q square is smaller than 0, so let's take these first two channels here, right? That means that the 1pi function, the self-energy, will be always real, right? In this case, this guy has no branch cuts, nothing, right? Because this denominator right here will always be positive if Q square is negative, right? M square is positive, so this is just analytic in all the domain, right? And so the function is real. Now, when Q square is bigger than 0, right? And specifically, right, if it just gets bigger than 0, still have no problem. But when Q square gets to 4m squared, right, you might remember that this x1 minus x is bound between 0 and 1/4 in this range of integration, right? When you get to 4m squared here, right, that means that this term can become bigger than this one, and then this logarithm develops a branch cut, right? So in the S channel now, let's put S channel here. Depending on the initial energy, right, you can have Q square big enough, right, so that this denominator in the log here is negative, right? And that happens once you hit Q square bigger than 4m squared. So let's start by looking at how this expression changes an electric potential between charges in the non-relativistic limit. So for now, I'm really concerned about these T and U channel, right? I have in mind on-shell particles exchanging photons in the non-relativistic limit. We have seen in quantum field theory 1 that the exchange of one photon, right? Just the simplest diagram you could imagine, this one, in the non-relativistic limit was related to the Coulomb potential. So I could write, here I'll write everything in momentum space because it's easier to incorporate this correction. We'll go back to position space when it is convenient, right? But this is what is obtained at leading order for QED, right? If you do the non-relativistic approximation. Now we have seen on the last video that one of the effects of this loop correction to the photon propagator is to replace this charge by an effective charge, right? Essentially, now what we have is a potential that is given by this expression. Let me write it here. So Q square 1 minus pi, that self-energy of Q square. And in this case, right, since I'm thinking on the T and U channel, right, this Q mu is given by, let's call P prime and P, the two momenta for the incoming particles, right? These can be written in the non-relativistic limit in this way, right? So Q mu will be the difference in momentum, but in this case, in the non-relativistic, you just have mass minus mass here in the first component, right? And these will be the rest of the Q4 vector. And that means that in this limit, I can write Q square as minus the module of the vector square. Right? And I'll substitute this here. Let me make some space. Let's then take a look on how this looks. So this is again the expression we need. Now I'm exchanging Q square by this minus vector Q square, right? Which happens here too. So I can put, let me change this to the vector square. There's a minus that goes here, right? And to start with, I'll take the most, drastic approximation possible, right? I'm going to the classical limit, so I'm thinking long wavelength for this photon. So all energies involved here are small compared to the mass of the electron. So I can expand this log in powers of Q square over M square and throw away everything but the leading order, right? So I can rewrite this log here. I just have to make the series. This will be x1 minus x Q square over M square, right? Plus order this thing to the fourth, right? And I'll disregard this part right here. This is a very rough approximation, but let's see what that gets us, right? So now my self-energy becomes just this times this one. So there's a minus sign that comes from here. This will be x squared 1 minus x squared times Q squared over M squared, right? And that's now easy to integrate. this will be just alpha q square over 15. The integral will just give me 1 over 30. And then there's a cancellation of that 2. You get that 15 here by m squared. Right? That's a very simple expression actually in this approximation. Now to know how the potential behaves, right? I have to plug this in here, right? And take the Fourier transform to position space. So let me write v of x as the integral in d3q over 2 pi to the cube exponential of I qx of v tilde of q, right? But v tilde of q is just plugging this expression up here. Let me do that, right? And that becomes just minus 4 pi alpha, which is just this e squared in the numerator here, over q square times 1 minus pi of minus q square, which is this expression. So alpha q square over 15 pi m square, right? So now again, I'm taking a very rough approximation here. So I can just take this denominator and expand again. I'm assuming this q square over m square is really small. So I just bring this guy up here. Oops, I lost a bunch of stuff. Let me put it here and change this sign, right? So again, I'm just approximating. But this is easier to have to make the Fourier transform, right? So you might recognize this 1 here is just 1 over q square, you see, which is the Coulomb potential, right? If I do the Fourier transform, I'll get another 4 pi. So let me bring this minus 4 pi alpha up front. And then the integral is just the Fourier transform of 1 over q square, which gives me 1 over 4 pi x, right? Like we did that in quantum field theory 1, right? Now the second part here, there's the q square goes away. You see, there's a q square here, a q square here, it goes away. So the Fourier transform will give me a Dirac delta, right? So let me copy the constants. There's a alpha 15 pi m square. And since q square is gone, this is just the Dirac delta of x. So now I can just simplify a little bit, and you see I have the Coulomb potential here, now written in position space and in terms of alpha, but it's the same thing we used to, right? Plus a correction. Let me figure out the corrections. Just there's a 4, some pi's, some cancellations there, but it's alpha square, right? 15 m square delta 3 of x. Of course, this Dirac delta is just because I'm doing a very rough approximation, right? The wavelength of the photon I'm considering is so big that it sees this correction as a happening only at one point, right? With no size. But that's an artifact of my correction, right? Another thing you can see here is that clearly this is a higher order correction in perturbation theory. You see this, the Coulomb appears as order at order alpha, and this new term appears at order alpha square, right? And this is called the Welling term, And what does it do, right? You can see clearly that this is localized at the origin of the potential, right? So if we were thinking in terms of, say, in a hydrogen atom, right? The change in energy induced by this change of the potential, so you could take the Coulomb part, it gives you the usual hydrogen atom levels, right? But now this correction, right, will be proportional at any particular state to this integral of the wave function square times this change in the potential, right? So this is the correction to the energy level. And of course, since this correction only cares about the zero component of this, right? So this is just minus 4 alpha square over 15 m square, right? Size 0. It will only affect states that have a non-zero component at the origin, and that means the S wave states for the hydrogen atom, right? This has been calculated, and it was another one of these calculations that were done really early, right, in quantum field theory, and motivated people to really believe in quantum field theory, because this correction right here is the size of 10 to the minus 7 electronvolt, is one of the many, it's actually small, but it's one of the many contributions to the lamp shift, right? So again, you see corrections coming from quantum field theory at loop level and contributing to observable quantities that people were trying to understand, right? Now, if we want to have a little bit more resolution on this new term, right, instead of just having a Dirac delta in the origin, I want to know how it behaves as I go close to the origin, right? I have to be less drastic with my approximation, right? Make a more careful approximation. In order to do that, let's write the non-relativistic potential again as the Fourier transform in 3 momenta q, right? 2p 2 pi cubed exponential of I q x, right? And rewrite the momentum space potential in its full glory. So there's a minus e square over q square 1 minus pi 2 of pi 2 of minus q square. Right, so that's what the integral we want to do. Here I'll define the module just to get a less cumbersome notation. I'll call big Q the module of small q, so I can exchange this by big Q. Here is the same q square. And up here I want to fully write this scalar product as qx cosine of theta, which is the angle between these two vectors. Now I can do this integral in spherical coordinates, right? This is just rewrite these in spherical coordinates and start integrating the cosine. That will give me, I won't do all the details of this calculation here. It's very similar to other calculations we did in quantum field theory 1, but it is in the lecture notes for quantum field theory 2, so you can look at the details there, right? This will become e square over 2 pi square. The integral in the module of Q, which I'm calling big Q here, so I have a dq, yeah, Q over Ix times the exponential of minus IQx minus exponential of IQx over Q square 1 minus pi 2 of minus Q square. Right, this is what I get after integrating cosine of theta, right? I can change here to have a integration in the cosine, and I'll get this big term. Now, these two pieces here, this one and this one, right? I can make them be the same. I just take one of them and take Q into minus Q, right? And I'll get an integral from minus infinity to 0, right, of the same integrand, and then I can put them together, right, to get something which is more useful. Let me move this definition up here and write the integral that I got. Hey, so I move an I outside, exchange E square for alpha pi x integral from minus infinity to plus infinity, because I made one of these two pieces to be integrated from minus infinity to 0, and then I glue them together. dq of q exponential I q x q square 1 plus pi 2 of minus q squared. And in this last step here, I did assume that pi 2 is a small correction to the 1 here, right? So this is the only approximation I'll be making in this calculation. I brought it to the numerator like that, right? Now, to do this integral, there's a pole here, clearly, right? And I also know that depending on the value for this big Q squared, this guy will also develop a branch cut, right? Starting at 4 m squared, right? So I need to really, to do this integral, I'll have to go to the complex plane, do this by residues, but I need to be very careful about the analytical structure of this integrand. So here I have extended Q into the complex plane. So this is the real part of Q, this is the imaginary part of Q, and we want to integrate along C1 in the bottom here, of course, right? So the first thing to notice is that pi 2 of minus Q squared develops a branch cut once minus Q squared is bigger than 4m squared, as we have seen before, right? Since I define Q squared in a way that Q squared is real, right? That means that it is the real part of Q will be 0, right, in order for this to be true, and the imaginary part of Q will be bigger than 2m, right? That's one way to see where this branch cut is. So it is already drawn here, right? And it starts at position I times 2m and goes all the way to big imaginary Q, right? So that's the branch cut. Another thing to notice is there is a pole at the origin here, right? For Q squared equals 0, we run through this pole. I don't want this pole in my way, so I'll move it up here to position I mu, which can be done just adding a term plus mu square right here, right? This is just to move the pole of the way. Eventually I'll take mu to 0 again and bring it down into the real axis after I do the integration, of course. So now, by residues, we know that the integral over this path I have drawn here, right, all the way around, right? So I'll write it like this: I alpha over pi x, which is this term here, times the integral in the whole closed path, right, of that complicated integrand. I don't care too much about writing it, right, will be given by the residue of this one pole right here, right, since it's the only thing inside the path of integration. So this will be I alpha over pi x, and then residues, right, 2 pi I times these calculated at the pole, which will be exponential of minus mu x, right? Let me try to show the expression up here, right? So you just have to calculate these at the pole, over 2 times 1 plus pi 2 calculated at minus I mu, right? And then, of course, when I take mu back to 0 at the end, right? Once I did this integral, I don't care anymore about the value of mu. I can take the limit of mu going to 0. Let me write it here. This becomes, right, this function is 0 at the origin, right, as per the renormalization conditions, right? This will disappear, the 2 here concealed, the pi concealed, right? What you get is the Coulomb potential. So this is the first thing we learn with this. Really, this pole is what is giving us the Coulomb potential. Let's see what the rest of the calculation brings us, right? So we know that this integral in the whole closed path is equal to the integral over C1 at the bottom, right? Plus the integral over C2 plus the integral over C5. But these two integrals, they are 0, right? Because if you look at the exponential here, right, this is goes to is suppressed for a positive imaginary part of Q. So this contribution will not matter. And of course, there's the integral C3 and C4, because I have to avoid this branch cut. I have to go around the branch cut, right? The potential I want to calculate, right, V of x, is, of course, this expression, right, which is only over C1, right? So I can write this as I alpha over pi x integral over C1 of that integrand, right? Which is, of course, if I isolate the integral over C1, I can subtract the integral over C3 and C4 from the full thing. But the full thing is just the Coulomb potential. So this is just the integral over the whole closed path, right? Minus the integral over C3 plus C4, right? And I'll call this last piece, right? Of course, I can call this the correction to the potential, right? Because it's, again, I'm finding that I have a Coulomb potential plus a new piece. And this new piece, it's important to see, is coming from that branch cut right there. That's creating a correction to my potential. Right? So now we have to evaluate this integral over C3 plus the integral over C4. Right? In order to do that, let's see what we have there, right? So essentially, you have one path that is coming from infinity down, right? But slightly dislocated to the right towards real values, right? So that's C3 is coming from infinity in the imaginary axis and going to 2m, right? But this epsilon guarantees that it is to the right of the branch cut, right? And I have some complicated, this is an integral over the q, right? And I have some function of q. C4 goes the opposite way, right? It starts from I to m and goes all the way to infinity along the imaginary axis, right? But now I have a minus epsilon that puts it to the left of the branch cut, right? That's how I avoid the branch cut. And here I have the same integrand. Now, I can do a change of variables here, just shift to get rid of these epsilons in the limits of integration. And this becomes just the integral from I alpha to I to m dq of f q plus epsilon. So I shifted the variable of integration in one way, and in this one I shift the other way. I also get rid of the limits of integration. So this is I infinity. I don't know why I wrote alpha instead of infinity here. This is infinity. Same here. I infinity. Okay. Of dq f q minus epsilon. So I shifted the other way. Right? Now the limits of integration look very similar. I can exchange these two in this way and get a minus sign in front, and you see that the total integral will be the difference of these two. Now I know that this branch cut is not coming from just, I know something about this function. If this was just any general function, it could be more complicated, but the branch cut is coming from a logarithm in there, right? And we know that in the case of the logarithm, the real part of f q plus epsilon is the same as the real part of this f of q minus epsilon, right? So since now I have a minus sign between them, the real part will disappear, right? But the imaginary part is not like that, right? In fact, the imaginary part has a sign now, right? That's this discontinuity of this function. Which means that together with this sign, the imaginary part will be added, right? So this will be 2i, the imaginary part of the whole integral from 2mi to I infinity of dq f q minus epsilon or plus epsilon, it doesn't matter, right? So what I'm showing is that the sum of these two integrals will be proportional just to the imaginary part of this integral right here, right? If I go back with that knowledge to this change in the potential, I can write it in this way, right? So the correction to the potential will be, let me copy it here. So I can write it again. So I have this piece here, right? And then this part 2i times the imaginary part, and now I'll write the integral in its full form, I to m I infinity dq, and now the function we had, it's the same we had above, right? Q exponential of I qx over q square plus mu square times 1 plus pi 2, and that's where the log is, right? Of, let me make it a little bigger, of minus q minus epsilon square, close all brackets here. There's even a bigger one out there, right? And that's the expression we're looking for. So now I have to figure out the imaginary part of this thing, right? Now we're far away from, we're not going near that pole, right? So I can throw the mu square away. That means I can do some cancellations here, which is convenient, right? So it really is this thing I have to integrate. I'll do, just for convenience, I'll define another q, let's call that small q, but it's not a 4 vector, it's just a number, right? Which will be minus iq. So remember, the branch cut comes from minus q square becoming smaller than 4, I mean bigger than 4m squared. That means that q squared will be bigger than 4m squared. That's what we're interested in, right, for this branch cut. But in terms of this new variable here, I can rewrite this this integral. There's some simplifications here too, right? I can drop these minus I together with this I and just write 2 alpha over pi x, the imaginary part of an integral. Now in terms of q, right, that's just from 2m to infinity of the q over q exponential of minus qx 1 plus pi 2 minus iq minus epsilon square, and close all the brackets, too many brackets. I hope I closed the right number. And that I can simplify to this expression right here, right? Since I'm only, and that's the advantage of changing to this variable. You see everything is real here, so I can take this imaginary part, come all the way and act it here, right? The number 1 has no imaginary part, so it's really the imaginary part of pi 2 that I'm interested in, right? So I can rewrite these as 2 alpha pi x integral 2m to infinity dq over q exponential of minus qx times the imaginary part of pi 2, and then I'll just simplify stuff here, q square plus I epsilon. And that's what I have to worry about. So pi 2 is given by, again, this expression, minus 2 alpha over pi integral from 0 to 1 dx x 1 minus x log of m square over m square minus x1 minus x q squared, right? And this only has an imaginary part, right? If this thing is negative, right? So if I call this this whole function f of x q squared, right? This will be this condition will translate to m squared minus x1 minus x q squared smaller than 0 generates an imaginary part for this f of x q squared, which is different from 0, right? If you look at this function, that happens only when this is negative, right? This looks something like that, right? This function at the bottom for a fixed value of q, right? For a fixed value of q, so this is x, and this is f of x q squared. That thing looks, not f, really this, just this part at the bottom here, right? This looks something like this, and I'm interested in this part. So there's a maximum x plus and a minimum x minus that generate an imaginary part which is different from 0. I can limit now my integration in x to that region, since I know I'll be taking the imaginary part of this function only. I don't care about the real part that comes from the integration in the whole range, right? It's very easy to solve this and find out which are x plus and x minus, right? So x plus minus is equal to half plus minus half times the square root of 1 minus 4m squared over q squared, right? That's easy to solve, right? And that means I only have to worry about this region. Now, I need to know the sign of the imaginary part. I know that the imaginary part of a log is just pi, right? But I need to know if this is plus or minus pi, right? So I'll define z, right? My z plus minus is equal, because I'm not calculating the log of this function. Remember, I'm calculating pi 2, not of q squared, but of q squared plus minus I epsilon, right? So if I substitute q squared plus I epsilon here, right, what I'll have in this argument of the log, I'll have this z plus minus here, which will be m squared minus x 1 minus x q squared plus minus I epsilon, right? And you see that I'm substituting z plus here, right? I'm just defining the two options. Why? Because it's easy to remember that if you take the analytic extension of z, right? Here's the imaginary of z, here's the real part of z, and you calculate the imaginary part of the log of z plus minus, this will be plus minus pi, because this log has a branch cut here, starting here, and the z plus is on that side and z minus is on this side, right? So that means that in our case, since we are putting z plus there, the imaginary part of our log will be just plus pi, right? So we want to use that now, right? And say the following, right? The imaginary part of pi 2 of q squared plus I epsilon, which is the thing we obtain, right, is just minus 2 alpha over pi. I'm using this expression here, right? Plus pi, because I'm taking this side of the branch cut, the integral in x from x minus to x plus, because that's the only region in which the log even has an imaginary part, right? So now I'm limiting my integral to that region, right, of 1 minus x, and that's it, right? Because the log is just a pi goes out of the integral, and now I just have to do this integral, right? This is pretty easy. I can do that by renaming x, doing a change of variables here. I take a y equal to x minus half. That makes this integral, well, the pi's conceal each other here. So it's minus 2 alpha integral. Now, when I do that, I eliminate that half here. So I just have, let me see, yeah, this square root, right? So half the square root, this one, right? And here I'll have minus half the other square root, right? dy 1/4 minus y squared, because essentially I'll have 1/2 plus y times half minus y, right? And that's easy to integrate. I'll get minus alpha. Am I missing any part here? No, it's fine. Minus alpha over 3 square root, right? The limits of integration. Let me put them here. 4m squared over q squared 1 plus 2m squared q squared, right? That's easy to integrate. You can check my calculus. I hope it's okay, right? So now I go back with this imaginary part that I calculated here, right? This whole piece, and I plug it finally in my correction for the potential, right? Which is here. So this expression I'll take down all the way here now, and I can put, so this minus goes in the front here, right? And the rest I plug right here, right? So again, I have this, I want to put a box around. It's a very important result. And we see here that this is next to leading order correction to the potential, right? It's proportional to alpha square, right? It's also sharply peaked near the origin because of this exponential over here, right? There's also 1 over q, right? But it's not just a direct delta. It's more complicated, right? So now I want to try to understand the effects of this guy, right, more specifically in 2 different limits. So the first one is for fairly large distances as compared to the only scale I really have here, which is 1 over the mass of the electron, right? In this case, if distances are big compared to this scale, you see that this exponential will be integrated from 2m to infinity, right? But if x is much bigger than m, most of the contribution of this integral will come from the lower limit, really close to the lower limit, because then this is sharply suppressed, right, by the exponential. In this case, that will be equivalent of taking q very close to 2m, and it is useful to make a small change of variables and rewrite delta x in terms of a variable that I'll call t, which is q minus 2m, right? I'll put that in the integration here. That becomes minus alpha over this, right? Integral from 0 to infinity of dt exponential of minus t plus 2m x over t plus 2m times all this, right? So alpha over 3. Let me bring this up. Square root 1 minus 4m squared 2m plus t squared. And here I have already I added these two numbers, is just t plus 2m squared t plus 2m squared plus 2m squared, right? So this is this last part. Now, since t is close to 0, right, I can do a bunch of approximations. So just taking t to 0 here just gives me 4m squared plus 2m squared over 4m squared. That's just 3/2. So this is just 3/2. This one I need to expand for t near 0. This is at first order t over square root of t over m, right? And here I can just disregard t, right? And then do the integration. So I'll have to do the integral. Now this is approximate because, again, I'm saturating the integral by the lower limit here, right? So this is, I just repeat. And now I have to do the integral from 0 to infinity of the exponential of minus t plus 2m x over 2m alpha over these 3 simplifies with that 3/2. So it's just alpha over 2 square root of t over m, of course, plus higher orders of t, right? This is an easy integral to do, right? You can just do it, and that will give us just, for x much bigger than 1 over m, right, delta v of x will be equal to, and now there are other simplifications here. I'm still keeping this alpha separated from this one because I want to extract the thing that looks like a Coulomb potential that is here, right? So this integral will give me another pi that conceals here, right? And then, in fact, I square root of pi, and what's left is this. The exponential of minus 2m x over m x 3/2. So you see, again, you have a Coulomb potential times a correction, right? Which means that the total potential, right, the full thing, let's call x, in fact, x is the module of the vector x. So just to give it more familiar form, I'll call it r, right? This is minus alpha over r, 1, which is the Coulomb potential, plus this correction, right? Which now I can add right here. Let me copy it. And this is the famous Welling potential, right? So you see, this is going to 0 really quickly for big R, right? And you go back to the Coulomb potential. But as you get close to the electron, suppose we have an electron right at the center creating this potential. As you get closer, since this has the same sign as the Coulomb potential, it is increasing the attraction or repulsion. In this case, I'm talking about an attraction, right? And the interpretation of this is, as you get closer to this charge which is sitting in the middle, so suppose we have an electron there, right? This guy is interacting with the electron-positron pairs that can appear here around it, right? In a way to polarize, right? The vacuum starts acting like a dielectric, because on average the positrons will be closer, they will be attracted, and they will be closer to these guys, to the electron in the origin, than the electrons will be. And that creates a cloud that is polarized in this way, right? So you can model this potential using that idea, right? And that's the interpretation. So you're getting enough energy in your photon that you become sensitive to this distribution around this cloud, right? Around the electron, which screens this charge, and it looks bigger and bigger as you get closer. Of course, this is made in this approximation, right? So as you get closer, eventually a potential is not a very good description. But we can do better, right? We can look at, as I said, the second region, right? First, we looked at this, right? And now we want to get real close, right? But in order to do that, it's better to stay at momentum space, right? But remembering that we're still in the T or the U channel, right? Which means big Q is really negative Q square, right? So I'll make these big compared to the mass scale I have now, which is the mass of the electron, right? Also, this interpretation, I forgot to say, is why we call that first correction to the photon propagation the vacuum polarization contribution, right? Because now you see it's like this charge at the origin is polarizing the vacuum around it, right? And creating this screening distribution of charge. So when you look from a distance, you see a smaller charge. This will be even more clear now. So in this case, it's easier to just stay in momentum space and calculate this guy directly, right? So for a big Q square, right, this guy will be approximately, again, I'm using the same expression we started. What happened to my alpha? Minus 2 alpha over pi, integral from 0 to 1, dx, x, 1 minus x, and then we have the logarithm, right, of m square over m square minus x, 1 minus x, q square. So in this approximation, I can forget this m square right here, right? And separate this log into many pieces. So I have a log of m square, a log of x, 1 minus x, another log of q square, and the only one I really have to integrate is the log of x, right? I can rewrite this as 2 alpha over pi. I brought some sign outside from somewhere, right? 0 to 1 dx, x 1 minus x times. So the log, that's where the sign comes from. I brought q squared to the numerator minus q squared over m squared. See, I inverted these logs. And then the log of the x part will be just ln. Let me use always the same symbol for log of x times 1 minus x. right? So now I can integrate this part. It's easier, just the integral of x1 minus x. And this one is kind of easy too, because I have the same thing outside the log, right? This will be just alpha over 3 pi. You can check the integration if you want. Minus q squared over m squared minus 5/3. That comes from this part, right? And now this expression, I can go and plug into the effective charge. If you remember, I had defined an alpha square effective, the running coupling, right, as alpha, really the number, right? I think there's a square here. No, this is just alpha, right? And 1 minus alpha 3 pi ln of minus q squared m squared, and I just exponentiated this part to include it here. Exponential of minus 5/3. And bring this guy inside the log, right? So I just wrote, I had defined this effective coupling as alpha over 1 minus pi 2, right? Minus pi, but pi 2 is the calculation I have up to order alpha, right? And now we have a actual expression for this effective charge, right? You can see here that this thing grows as I go to smaller distances, right? Or bigger q squared, right? So if I write this in terms of the distance, so big distance, small distances mean big q squared, right? This will look like alpha effective, right? And I put here like log of r. This will look something like, at really big distances, or q squared is small, right? I can forget this contribution and it's just 1 over 137, right? But for small distances, this guy, let me try to make a plot of this. It blows up. It becomes bigger and bigger, right? As you get to really small distance, big q squared, because eventually these numbers starts getting close to 1, right? And these blows up, right? We can even calculate how this blows up, right? So just to give some numbers, right? Just to give some numbers, if I take alpha, this constant, equal to 1 over 137, which is how we measure it, right? For big distances. So we were, classical physicists were operating in this limit, right? And now bring it down, I can, as long as this is still a small correction, I can bring it to the numerator, right? I can take this 1 minus and become a 1 plus here. This alpha effective will be just alpha times 1 plus alpha over 3 pi log of minus q squared over m squared exponential of 5/3, right? And now we can put some numbers here, right? And see that since this is 0.0008, right? So you see this correction, this thing needs to get really big to compensate already for this such a small factor, right? And since the momentum is inside our log, This is really difficult, right? You see why people never noticed the running, right? The change of this effective interaction as they changed energies on this limit, because you have to change the momentum a lot. Also, the momentum is here multiplied by a fairly small number, right? This is 0.19, right? It's divided by the mass of the electron, so that sets the scale of momenta. You really have to go towards relativistic energies to even notice this is around, right? Otherwise, you just think your constant is a constant, right? The alpha is a constant. You won't notice anything. In fact, we could ask, right, when this breaks down, right? Because this is a correction, this is the one loop correction, right? It's supposed to be small compared to the three-level contribution, which is this part, right? When this guy gets so big that it's comparable to this one, it also means that the two-loop correction will be comparable with the one loop, the three loops will be comparable with the two loop, because the coupling itself is increasing. You can think about this being the parameter of expansion even, right? So when you can estimate when will that happen, right? Just taking this one and asking, when is this true? Let me copy this here, right? Plug the numbers here and solve, right? It turns out that this is true for q square of the order of minus 8 times 10 to the 554 gigaelectron volts square, right? Since I'm talking about q square. So you see, that's an energy that is so big that I don't think we have really to worry about it. But this is the so-called Landau pole of QED, right? It's when perturbation theory fails. It doesn't matter that the coupling, the effective coupling, really goes to infinity. It just means that this perturbative calculation that we are doing cannot be trusted anymore, and you have to do other kinds of approximations. You won't be able to do perturbative theory anymore, right? And of course, this energy is far beyond where QED is valid, right? Way before that, we have electroweak unification, right? You start having W's and Z's that will also contribute to the photon self-energy, other quarks, you name it, right? So, and the Planck scale, so it's really only a theoretical pole, because you never get to that using QED, right? It's far beyond our reach. But suppose we lived in a universe with just electrons and photons, then the interpretation of these would be a continuation of the interpretation of the Welling potential, right? As you get close, right, you're penetrating that cloud of screening electron-positron pairs, right? Virtual electron-positrons being produced in a vacuum and immediately polarized by this charge in the origin. And as you get close to that, almost like a singularity, right? Like the bare charge in the center, right? The interaction keeps growing, right? Because you're penetrating more and more in that screening, to the point that eventually your theory is not perturbative anymore. The charge, you're seeing this bare charge, which seems to be really big, right, in this interpretation. So at some point, even QED would become a strongly coupled, right? So that's what we're seeing here now, and that's what we call the Landau pole. So that's what I wanted to talk for today. Next video, we'll talk about another loop in QED, which is the electron self-energy. See you then.